Now here you would see that even before I enter this do loop where I keep on iteratively correcting the value of or improving the value of y for all the i's, you can set a variable LL, some dummy variable, equal to 0, and every time this is repeated. So, if this condition is not satisfied, then it will go back here, then you update LL equal to LL plus 1. What is the advantage that you get? Once it comes out of this loop, once this condition is satisfied, you get to know in how many iterations you get a solution to the differential equation. Now, this method is called the Jacobi method. The Jacobi method to calculate the solution of the difference equation. What you have done is essentially using these two relations, you have substituted d2y dx2 and dy dx in the differential equation. You calculate yi for each of the I values, right. Then you save this new values obtained of yi into y old and use y old to calculate the new values of I iteratively, right. Now, the question is, what limit should you set here? So, I said 10 to the power minus 3, it was arbitrarily chosen. Now, the expressions that you use here, they have errors at the order of h cube, where h is the size of your the grid points, basically x 2 minus x 1 or x 3 minus x 2, right. So, if the error anyway is the order of h cube, you choose h equal to 0.05, there is no point in setting this limit to be 10 to the power minus 8, because anyway you will have large errors, orders of h cube. So, you are never going to get a convergence if you expect that you shall accept the value if this limit is 10 to the power minus 8, only if this condition is satisfied for all the values of yi minus y old for all values of I, and if limit is equal to 10 to the minus 8, you are never going to get it. You do expect an error in the value of yi for each value of I order of 0.0025, because h is equal to 0.05, right, h square is 0.0025. So, there is no point in setting a limit lower than this value. You are not going to get a converging solution, right. The other point is that in the Jacobi method, you were calculating y at each point in I, saving it into y old, and you were using yi to calculate, and you are using basically y old at I plus 1 and I minus 1 to calculate yi. Now, while you are updating yi from say y equal to 2, I equal to 2 to I equal to NOP minus 1, right. Before you update y at I, you already have the updated value of y at I minus 1. Now, in this expression, y old at I plus 1 you do not have yet when you are running this loop, right. Here both were old, but as you are updating, you already, when you have reached I, you already have the new value of yi, and in this expression, if you use the new value of y I minus 1, then it is called the Gauss-Seidel method, and this often leads to a quicker convergence of the solution. Okay. Now, you cannot use y old the new value of y at I plus 1, this you do not have access to, because you are basically changing I from 2 to NOP minus 1, but you do have an access to the new value of y at I minus 1. So, that is the only expression that I have substituted here in this expression. Xi of course does not I mean it is independent of the iteration, it is basically just dependent upon I and not upon the iteration, but you can get more accurate values of y I and your solution can converge in a quicker manner if you use the Gauss-Seidel method. Okay. Now, with this background, let us actually go to the code and see how this has been implemented and have an idea of the solution. Okay, so here is the code, program diff equation, and then basically you have the obvious implicit none, and this is where I have defined the interval f x is 0. So, that is one end of the interval, and end x is 1, the other end of the interval. Dx or h I have set to be 0.05 as we were discussing in class. Number of points between the two endpoints is number of points is basically end x minus f x minus d divided by dx, right. And here you have some arrays defined. The arrays, the size of the arrays is y old and y, and the length of the arrays is number of points. So, if you change h to say or dx to 0.01, then the size of the array automatically changes. So, if you have h or dx equal to 0.01, then the number of points between the interval will be 100 and NOP will be 100. Right. Now, these are those dummy variables called d1, d2, d3, right, which shall sit in front of the which will be basically prefactors in front of y I plus 1, y I minus 1 and so on and so forth. So, those have been defined right at the beginning of the code, so that you do not have to calculate it multiple times. Now, here is a convergence criteria, limit equal to 0.0025, because I have set h equal to 0.05. Here is your LL, which will give me in how many iterations the code has the code has achieved convergence for a particular value of h, right. And this is the condition, the variable whose value decides whether you are going to exit this open ended do loop once the system has converged, right. Here I am specifying the boundary condition that y equal to 1. So, the number of grid points is number of points basically NOP, and y at 1 is 0, right. At x equal to 0, y equal to at x equal to 0, I equal to 1 and y is equal to 0, and at x equal to 1, I equal to number of points NOP and y is 100, and I have chosen a straight line, right, as the initial condition. So, that is what I am doing here. I am setting up the grid, the value of xi for the different values of I by setting dx, right, x equal at I equal to 1, x equal to 0, at I equal to 2, the value of x will be 0.05. So, that is automatically set here, and the value, the initial guess of y over the entire range is basically set here, right. It is basically a straight line with the appropriate slope. And y, so basically y2 minus y1 divided by x2 minus x1, and that is exactly what is written here, and the value of yi is basically y equal to mx, this equation of a straight line. So, for each value of xi, the value of yi has been calculated, nothing more than that, and here is the actual do loop, right. So, LL has been set equal to 0 right at the beginning of the code. So, this is the do loop to the open ended do loop, LL equal to LL plus 1. If condition remains equal to 1, then exit. This I have written right at the beginning, and here is where I write y old equal to y. This is the actual line where you update the values of y, where I am using y old at I plus 1 and y old at I minus 1 and x I. At the end of this step, I have the updated values of y over the entire range at each of these grid points, and I set cond equal to 1 and do I equal to 2 to number of point minus 1. At each point I am checking if the absolute value of y old minus y I is greater than the limit, then I set cond equal to 0. This is the condition to check convergence, right. And here I write down the number of iterations required to achieve convergence, which is LL. Once it has come out of the loop, I have a fixed value LL, and I write down the value of xi and y over the entire range, and I plot this, right. So, I compile this differential equation. So, I G Fortran. So, this is your compilation of this code, and basically what I have done carefully is that for a particular value of dx or h 0.05 and limit, I have saved, I am going to save the value of the solution x and y for different values of I in this file, right. So, if I run it, you see that I have essentially 20 grid points, and the number of iterations required to achieve convergence was 623. Now, suppose I changed this to, now suppose I say, well, I choose my h to be 0.01, but I keep the same convergence, right, because it's the same. And then of course, I want to change the name of the file where I am going to store the data, right, because I want to compare the data for these different values of h and the convergence factors. So, here what I have said is I am not going to change the limit, but I have changed the value of h, if you like, or dx if you like, and I compile it again and run it again. Here now I have 100 points in the between x equal to 1 and x equal to 0, and now I needed 7002 points, 2 iterations to get converged to the right value, right. Now, what happens if I, so now I have a smaller value of h, the tolerance should be even less. So, here I am changing, so I am keeping dx to be the same as 0.01, but this limit I can easily change to, where am I defining limit? Yes. So, I am changing the limit to h square again, right, and then I must change the name of this file as well, because limit has been changed. Dx remains the same as before, and if I compile it and run it, it needs 17,386 iterations before it converges with a lower tolerance, because I have lowered the, because I have a smaller value of h, I have also lowered the tolerance for it, right. And now I can go to even smaller values, suppose 0.0, 2 zeros as 1 and 1. So, 10 to the power minus 3, and I set my limit as just 10 to the power minus 5, say, right, though I can set the limit to be 10 to the power minus 6 as well, but I just choose to cheaper higher tolerance, and correspondingly I am changing the name of the files where dx equal to 0.001 and the limit is point. So, I am not explicitly written the point as 0.00001 10 to the minus 5, right, and if I run it, it does take, so number of grid points is 1000. So, the range between x equal to 0 and x equal to 1 has been changed, has 1000 grid points. So, basically the number of y calculations have significantly increased at each of these points. Moreover, the number of iterations required to basically converge to the right value with a higher accuracy, because I have both decreased h and hence I am allowed to decrease the tolerance, and it requires nearly 10 lakhs, right. This is 10 lakh iterations to reach the required accuracy. Basically, it keeps on iterating it so many times before it converges, where the difference in the values of y old and y I at each of these I points is less than 10 to the minus 5. So, this is supposed to be a much more accurate value. Now, if you had Gauss-Seidel, so what would be the difference? Just all that you have in Gauss-Seidel is basically the previous code. It is just that if you compare this y old, right, has been changed by to y I minus 1, because in the previous iteration when I run a loop from I equal to 2 to NOP minus 1, I already have the new updated value of y at I minus 1, though not the updated value of y at I plus 1. So, here I use the old value, but here I use the new value of y I, and this is the only difference between Gauss and Seidel. And you can do the same thing, and you will see that it will have a lower number of iterations to reach the converging value, the converged value. I have already done that and I have plotted it for you, right. So, here what I have done is solution of the differential equation with boundary conditions with h equal to 0.05, 0.01 and 0.001, and here I am plotting y as a function of x versus x, and this line is your initial straight line, which was the guess with the values of y that I calculated for each value of I, which was the initial guess bit for basically x equal to 0, y equal to 0, and at x equal to 1, y equal to 100, right. And if you have h equal to 0.05 and the limit is 0.0025, basically h square, this is the solution that you obtain after a certain, I think 673 iterations or so, as we saw previously, right. Now, as we change so, when h equal to 0.01 and limit is 0.0025, you have this red curve, right. So, this I have made more accurate, but I have not changed the limit. Then you have essentially this red curve. When I change h equal to 0.01 and limit equal to like 10 to the minus 4 corresponding to h square, you get this green curve. And when you have essentially h equal to 10 to the minus 3, right, and limit you set to be 10 to the minus 5, and it ran for 10 lakh iterations, if you remember, then you essentially have this blue curve, which you can expect to be the most accurate. When you have h equal to 0.05, of course, you have discretization errors here, hardly surprising, right, because you have only 20 grid points between 0 and 1, but when you have h equal to 0.01, your convergence might take more time, but it will be more accurate, right. And when you have h equal to 0.001, your tolerance is even lower, and this blue one is expected to be the most accurate data, right. So, you can try this out for various values of h and tolerance. Of course, there is no point in setting tolerance much lesser than h square. Now, the last thing I want to discuss in this class is that since these expressions of y dash and y double dash are accurate only as h, the error is in h cube, then suppose you had a need to calculate more and more accurate values of the solution to the differential equation. Of course, one method would be to go to lower values of h, and you already saw that over such a small range and for a relatively simple differential equation, it took quite a few seconds, around 10 seconds to get the solution. And especially if you now increase the range and have more complicated differential equation, it would take more time, right, as you decrease and decrease h to get to the accurate solution. Is it possible to have a higher value of h, lesser number of grid points, but yet obtain a more accurate solution y as a function of x at each of these grid points? In that case, you basically what you need is more accurate expressions of y dash and y double dash, so that you can use higher values of h without compromising on the accuracy, or you can have lower tolerance. And more accurate values of dy dx and d2y dx2 have been derived in this book that I have already referred to, Diffries and Hasburn. You can look up the derivation, and what you have is dy dx can be written as y at x minus 2h minus 8y x minus h plus 8y x plus h means, and y at x plus 2h. So, previously all the expressions were calculated from just the first neighbor on the left and first neighbor on the right. On the other hand, here what you have to do, you are taking the help of the y at a grid point 2 points removed, 2 points to the left and 2 points to the right. So, right. So, you are basically calculating, you are averaging dy dx over a larger range in the grid point, right. And of course, this can be written as y I minus 2, and this will be written as y I minus 1 and I plus 1 and so on and so forth. And when basically you are calculating the new value of y I, you have to use the old values in the Jacobi method, and for some cases you can use, for the Gauss-Seidel, of course, you can use the updated values. Similarly, the expression for d2y dx2 is this. Again, it depends upon x minus 2h. So, basically 2 points removed to the left and 2 points removed to the right, and you have these prefactors here, right. And this expression, so the expression here and here, they are accurate to the order of h to the power 4. So, the error is you are neglecting higher order terms in the Taylor expansion. This is nothing but the way it is obtained is basically Taylor expansion, and you basically match coefficients and neglect terms at the order of h4. So, that is where the error will come in. And basically what you have to do if you had wanted a higher accuracy is calculate d2y dx2, well, substitute d2y dx2 and dy dx in this differential equation, whichever one you have to you want to solve, right. And now similarly there are expressions for d3y dx3 as well, and what you have to do, then you will get an algebraic equation and then solve for y I, which of course now will be written in terms of y I minus 2 and I minus 1 and I plus 1 and I plus 2, right. So, when you actually use this, there are some other subtleties, but if and when you need to use it, you can learn those up. Remember that since you have x minus 2h or I minus 2, so then you have a, so if you want to calculate the new value of y I at just next to the boundary. So, suppose y I equal to 1, the value of y is specified, it does not change, but at y equal to 2, here it depends upon I minus 2. So, basically I goes as minus 1, which is ill defined. So, there are some issues of how to solve it, and similarly you will have a similar problem when you do I plus 1, especially again near the other boundary, but there are methods how to solve for it. I am not going to discuss this over in this lecture, right. When you need it, you can learn it. That is anyway the scope of this course, that we are giving you an introduction of how to develop different algorithms, so that whenever you need to know more about a topic, you will read it up, learn it and implement it in the computer, right. With this, I shall end this class today. Thank you, and in the next class we shall discuss partial differential equations. Thanks.